Good morning. Today we will discuss Module 1. In that Module 1, Introduction, a digital signal processing system, the sampling process, discrete time sequences, discrete Fourier transform DFT, and part Fourier transform, and linear time invariant systems, digital filters, estimation, and interpolation. Here we will go first to discuss the Module 1, Introduction to digital signal processing. Okay, here the first topic is a digital signal processing system. This is the block diagram of digital signal processing, which consists of anti-aliasing filter, analog to digital converter, DSP processor, digital to analog converter, reconstruction filter, and this is output, this one is input. Here in real life we have the signals in analog form. Okay, therefore that analog signal can be converted to digital using the digital to analog to digital converter. Why? Because the processor which can process only a digital signal. That's why we convert the analog signal to digital signal. Okay, directly we won't convert the analog to digital, but we can convert it. We can do the sampling of the analog signal. Can do the sampling. Before sampling, we can remove some signals, signal components. Its frequency more than fs divided by 2. Okay, then input to the analog to digital converter is samples. Then here we'll get the output of the analog to digital converter is digital. Okay, we can make it quantized. We can do the quantization. Then that input digital signal send it to the digital processor, digital to signal processor. Okay, after processing, output of the DSP is digital signal. Okay, then that digital signal is converted to analog. Then we can see here, briefly explain about this. A DSP system uses a computer or a digital processor to process signals. The real life signals are analog and therefore must be converted to digital signal before they can be processed with a computer. Okay, to convert a signal from analog to digital, an analog to digital converter is used. Okay, after processing the signal digitally, it is converted to an analog signal using a digital to analog converter. Here, the DSP system which consists of some additional blocks. What are those? Anti-aliasing filter and reconstruction filter. Okay, anti-aliasing filter for filtering the signal before sampling, and the second is the reconstruction filter placed after the digital to analog converter. The anti-aliasing filter ensures that the signal to be sampled does not contain any frequency higher than half of the sampling frequency, fs divided by 2. If such a filter is not used, the high frequency contains sampled with inadequate sampling rate, generate low frequency aliasing noise. That produces the, if the signal components which has the frequency more than fs divided by 2, then what will happen? Low frequency aliasing noise is generated. The reconstruction filter removes high frequency noise due to the staircase output of the digital to analog converter. Okay, an analog signal is a continuous amplitude signal that occurs in real systems. Such a signal is defined for any time and can have any amplitude within a given range. The sampling process generates a sampled signal. A sample signal value is held by a hold circuit to allow an analog to digital converter to change it to the corresponding digital or quantized signal. Here, when the input signal for the analog to digital converter is sampled data signal. Output is digital signal. Okay, this is the continuous signal. Okay, this is the output of analog to digital converter. Sample signal. So this is sample data signal, and this is analog to digital converter output and quantized. Okay, then this one is output of the D bar A staircase output, DAC output. The digital signal can be processed by a DSP and is the input to the D bar A converter. The analog output of a digital to analog converter has staircase amplitude due to the conversion process used in such a device. This is about the digital signal processor block diagram. Okay. Next, here we will discuss about the sampling process. The process of converting analog signal to digital signal involves sampling the signal, holding it for conversion and converting it to the corresponding digital value. When you are converting analog signal to digital, okay, which involves the sampling the signal. Okay, the sampling frequency must be high enough so as to avoid aliasing. Aliasing is a phenomenon due to which a high frequency signal, when sampled using a low sampling rate, becomes a low frequency signal that may interfere with the signal of interest. This definition is very, very important. Please go through this definition. Aliasing. Anti-aliasing means which can avoid the high frequency components. Okay, that means the frequency components more than fs divided by 2. Okay, to avoid aliasing, the sampling theorem states that the following requirement must be satisfied. It is fs equal to 1 divided by 2 greater than 2f maximum. Fs is sampling frequency in hertz, t is sampling interval in seconds, and f maximum highest frequency contents of the analog signal. So here, for instance, if we sample a signal with its high frequency content as 10 kHz, it must be sampled using a sampling rate of more than 20 kHz. Highest frequency, this one is f max. 2 times f max is 10 2 into 10, that means 20 kHz. That means the sampling frequency is 20 kHz. In order to satisfy this requirement, an anti-aliasing filter is used. This filter limits the frequency contents of the signal to satisfy the sampling theorem. That anti-aliasing filter limits the frequency contents of the signal to satisfy the sampling theorem. The actual sampling frequency must be higher than this theoretical limit to avoid tight constraints for the implementation of the anti-aliasing filter. And the next topic is discrete time sequences. The result of sampling an analog signal is a sequences representing the signal samples. The sequence that results depends upon the signal that is sampled. Here, the x of t equal to a cos 2 pi ft. This one is analog signal. Is sampled using t. Okay. After sampling, we'll get x of nt equal to a cos 2 pi f n into t. N is equal to 0, 1, 2 and so on. For simplicity, the sequence x of nt is denoted by x of n. X of n is equal to a cos 2 pi f n into t. Since the sampling frequency fs equal to 1 divided by t, fs equal to 1 divided by t, and substituting theta for 2 pi f into t, 2 pi f into t. Then here we'll get x of n equal to a cos 2 pi f n into t. Okay, t here 1 divided by fs, this one t equal to 1 divided by fs. I have written here a cos 2 pi f into n divided by fs. Okay, here we know that what is theta here, 2 pi f into t, right? A cos theta 2 pi f t, which left here n, a cos theta n. Okay, the quantity denoted by theta is called the digital frequency. Note that the unit for the digital frequency is in radians. The general equation that relates the digital frequency to analog frequency is theta is equal to 2 pi ft. What is t here? 1 divided by fs. 2 pi f divided by fs. Note that the digital frequency range for a properly sampled signal as obtained from equation number 5 is from 0 to 5. Okay, this theta is 0 to 5. The above x of n sequence called the sinusoidal sequence occurs frequently in DSP system. Okay, another important sequence that arises in DSP scheme is complex exponential sequence. It is p of n equal to e raised to j 2 pi n divided by capital N, where n equal to 0, 1, 2 and so on, where n is an integer. Here the exponential complex exponential sequence. Okay, p of n is equal to e raised to j 2 pi n divided by n. Okay, one more here sequence is a sequence that repeats is called a periodic sequence. That means here periodic sequence results from sampling periodic signals and satisfy the following relation: x of n is equal to x of n plus n. Yeah, what is periodic signal? For example, if you consider 1, 2, 3, 4. Same sequence can be repeated again. 1, 2, 3 and 4. Again 1, 2, 3, 4. Same sequence can be repeated, right? Here, here and here. This is called periodic sequence. This is called periodic sequence. Okay, it is easy to show that the sinusoidal sequence x of n above has a period f divided by fs, and the exponential sequence p of n has a period equal to n samples. Okay, the frequency response associated with the time domain n point sequence x of can be determined from the frequency response. That is what we discussed here till now. Those are time domain sequences, time sequences. Now the frequency response x of e raised to j theta is equal to n equal to 0 to n minus 1 x of n e raised to minus j n theta, where theta is the digital frequency which range from 0 to pi radians, corresponding to the analog frequency from 0 to fs. The theta is vary from 0 to 2 pi, and the analog frequency is from 0 to fs. The frequency response is a complex continuous function of theta and provides both the magnitude response and the phase response. Next, I will discuss about the DFT and FFT. What is DFT? Discrete Fourier transform. FFT means fast Fourier transform. Discrete Fourier transform means conversion of time domain sequence to frequency domain. That is DFT. IDFT means inverse discrete Fourier transform. IDFT means conversion from frequency domain to time domain sequence. That is IDFT. Okay, here the FFT, fast Fourier transform. Here these are the algorithms to compute the DFT. Compute the DFT. The DFT pair here it consists of x of k. X of k is equal to 0 to n minus 1. X of n e to minus j 2 pi n into k divided by n, where the k is varied from k equal to 0, 1, 2 and so up to n minus 1. And inverse discrete Fourier transform, x of n is equal to 1 divided by n, summation of k equal to 0 to n minus 1 x of k e to j 2 pi n into k divided by n. Okay, here e to j 2 pi divided by n is called as Todel factor. Just remember that e to j 2 pi divided by capital N. This one is called as Todel factor. E to minus j 2 pi divided by n. E to minus j 2 pi divided by n. That is Todel factor, Wn. To write this equation, x of n is equal to e to minus instead of e to minus j 2 pi divided by n, I will write Wn. What left is n into k, right? Write n into k. Okay. Thank you.